Okay, let's start. So first of all, I want to thank you for coming to this talk. The competition right now is fierce. Andrei Alexandrescu and Ben Deans against me. Whew. And you're still here, so thank you. Clap. It's good to see that people like Python in the C++ conference. So we're going to talk a lot about Python. We're going to see Python code. We're going to explore how to make those things work together. And I worked really hard today to add reflections. So we will see reflections as well in Python bindings. Let's start. So we will do all those things that I said. I just love LLMs. And I'm showing this and I'm talking about this because LLMs are basically powered by Python, C++, and CUDA. Everything runs on Python because it's easier, but behind the scenes, everything is binded to C++ and to CUDA, and it's really easy, and we will see how to do it exactly. This part of the talk, I call it shameless. I present myself and I show the things that I do. So I'm Alex Dathskovsky. I have more than 17 years of experience in system software development. I worked in many different kinds of systems, from defense to medical systems, worked in an ASIC that accelerates data, and right now I just started a new position in CppyDB, which is basically a database that replaces Cassandra, and it's on speed, like 20 times faster than Cassandra. Just pull it into your system, and it works the same. I have a very active LinkedIn account where I speak about C++. I try to show how things work, but I have some riddles there, so if you're really mad at people that do riddles, you have to know that I do them sometimes. I have a blog, CPP Next, where I can do more in-depth things about the things that I do in LinkedIn, and I have a YouTube channel. So after the talk, please like and subscribe to the channel. I already have 14 or 16 videos there, so I'm working hard to make it something that is maintainable and to do something that will contribute to people. And beside that, I'm part of the CPP committee and standardization committee, of course. And now we can begin. So let's start with a survey. Before I started writing this talk, I decided to do a survey to ask people, C++ developers, what is their second most used language? I did it on LinkedIn, and I had around 600 people, 600 C++ developers that actually answered me. So as you can see here, Python is #1 language for C++ developers. So if I'm doing something else that is not C++, it will be Python, not C, which is pretty nice. Then I remembered, wait, isn't there some survey that already does that? I don't have to do that. So C++ standard survey does that. I found it, this is the latest one, and around 2 times more people answered there. So you can see still, Python is the #1 language. And it's almost a slideful, because more people that use C++ use Python. In my opinion, we should start saying C++/Python and not C/C++. That annoys me in any case, but Python fits here well. So why C++? Well, that's a ridiculous question. We love C++. We love to suffer with C++, but it's a good language. We can do a lot of things with it, and this is a C++ conference after all. Why Python? Python has many good things to it. For example, if you want to do fast development, it's really easy to do it in Python. What do I mean with that? If you need to do a POC, it's really easy to write Python code fast. You have many different libraries in it. You can just push everything together, do something dirty, quick and dirty, and you have your POC done. Now we can do something about performance. It has simpler interfaces. It's easier for people that are not programmers, for example, algorithm people, to write code in C++. It reminds them of MATLAB. And it's an interpreter language, so we don't have to compile. I don't know about you, but when I compile, especially on a laptop, that's 45 minutes that I do nothing, because the laptop is dying. When I use Python for everything, that's really easy. It goes around. I can do code debugging. I can do new code. I can write in a Jupyter notebook and do code blocks. And that works just great. And it's really easy to do algorithm prototyping. Because Python and C++ are so close, as I showed you, and more people that use C++ use Python, and Python people, I guess, they see C++, they're starting to be very similar to each other. So in this part, I wanted to show you parts that in C++ that's starting to look more and more like Python. In Python, we have a very easy way to print and format strings. So here we're just formatting a string with a tuple and a number. Everything works in the interpretation, and we get a very nice print. In C++, we have the FMT library. We have the stud print as well, but I wanted to show something that will work if you don't have C++23. Here, basically, we can see that we can format the strings almost the same way like in Python. So we're using a tuple, and we're using a number, and we get the same print out. In Python, you can format containers in a very easy way. So here we have two containers. One is a list, and one is a dictionary. And when we print them, we can see a list and a dictionary without doing a lot of things, just throwing objects at it. In C++, with FMT and stud print, we can get the same effect. So we are printing an array, and we are printing an unordered map, and we get the same print exactly. That is pretty nice. That is easy. In Python, you could always return more than one parameter. Basically, you had binding to parameters since the beginning. So here we are using a function that returns 3 parameters. The parameters it's received, and it does a plus b, returns the full function. Then we are binding the parameters to a, b, c outside the function, and then we are printing it. Pretty easy. In C++, we can do the same thing. So right now, we can return, since C++11, we can return tuples out. Tuples is exactly what returns in Python. But here we have to be more concrete. We have to say that we are returning a tuple out of this mechanism. When we are using it, since C++17, we have structural binding that looks almost exactly the same like in Python. We just need the brackets around the parameters and the auto, and the usage is almost the same. Then we can print it, it looks the same, and it feels almost the same. The printout is exactly the same. In Python, we could always run on for each functions, on for each loops, on containers. It was really easy to do it. And in C++, in C++11, I hope everyone knows that we have for each or ranged fors. And I hope you're using them and not indexed fors. But the more interesting thing about Python that we had the enumerate function. Enumerate function is basically a generator that yields the value and yields the index in the same time. So it was really easy for us to go over a container and print the index of the value and the value, or to do something with those things. And that's what we're getting. In C++, since C++20, we can initialize a value inside the for loop, inside a ranged for loop. So here we have an example where I initiate I inside the for loop, run over an array, increase the I inside this function, and print out the values. And as you can see, we got exactly the same typing as if we are using Python. But that's not exactly the same, right? That's not exactly the same. We want something that looks and feels like a real enumerate. So since C++23, basically since C++20, we could do it, but we didn't have the tools. We just had coroutines, and we could write something by ourselves. In C++23, we got generators. So basically, we got the tools already to do what we want to look more like Python. Here I'm creating a generator that will return a tuple of 2 ints, and it receives any container inside it. It initiates index, then does a for loop, a range for loop on the container, co-yields for each value, adds to the index, and returns v with it. Because it's a post increment, it returns the value, then increases it. Then, when we are using it, it almost looks exactly like Python right now, because we are binding I and v, and we are using enumerate function on our container, and we are printing. So it looks almost exactly the same as Python does. And we get exactly what we wanted. In Python, we could always ignore values. So here we have the function that we already wrote that returns 3 values out. But the first 2 values are not interesting. So we're just ignoring them, and we are taking just the third value, and that's fine. The underscore used to do the work for you. In C++, you could do the same thing with std_type, but it looks cluttered. Who used ignore in his life? Wow. Usually when I ask this question, I get one hand or something like that. So ignore is with us since C++11, but still majority of people don't know about it. Ignore is a neat way to say, I don't care about it. It gets any variable in, and it just ignores it. And C is something that we actually want to bind. But it looks cluttered, right? It's not exactly the same as Python. We write a lot of letters here, and it's yucky. In C++26, we finally have the underscore. So we can bind to an underscore. And look, the code looks almost exactly the same as Python does. We have the underscore. The only thing that is different is, again, it's the auto and the brackets. In Python, it's really easy to work with functional programming and ranges. So here you have a one-liner that creates 20 values of random uniform numbers. Then it filters out the numbers that are larger than 5 and smaller than 9, and creates a new range. Then we're printing the range here. For some reason, all the numbers are the same. I don't know why. Uniform. In C++, we could do the same. Because we have seen C++20, we have ranges. So we can do more things that look like that. Let's ignore lines 42 to 45. It's just a way to do random numbers in C++. But line number 47 uses ranges to initiate the vector. It uses the distributor and initiate each value of the vector with the vector for, ranges for each. Then we're using format fmt print, and we're using nums that we created, pipe operator, and we're saying we want to filter that numbers to the same thing, numbers that are larger than 5 and smaller than 9. Looks simple, and that's exactly what we want. But we can do much more than that. This example, I thought about it, it's not the best example. Do you know why it's not the best example? What do you know about stud views? They are busted. So basically, using stud views are problematic because they are views. If someone removes your numbers or objects behind your legs, or you will not know that, and you will have problems, undefined behavior. So you have to be really, really careful when you're using views. But it's really, really nice to see how it works here, because this code takes a lambda that calculates if something is an odd number. It creates 30 numbers, pipes it to a filter that filters out odd, pipes it to a view that takes 10 first numbers, and pipes it to something that reverses the numbers, and then prints it out. And we got exactly what we wanted. So 3 lines of code equals around 25 lines of code if we reuse iterators. That's cool, right? That saves us a lot of time, and it looks more like functional programming. So functional programming is a great thing to use. Okay, so C++ is becoming more and more like Python. And Python is great. Why can't we just use Python? Why do we need C++? Why do we need other languages? And the reason is the greatest achievement of this language is the greatest downfall. It's interpreted language. And it means it's slow. It's really, really slow. We cannot do something in production if we need performance. And if it's slow, we cannot do anything with it. So besides being an interpreted language, it's a dynamic language. What does it mean to be a dynamic language? It decides about variables and parameters during runtime. It doesn't know anything about them, so it can do a lot of things, expand numbers, decide something for you, and it's really easy. People are saying it's easy in C++ to shoot yourself in the foot. In dynamic languages, it's much, much easier. Let's talk about the problems that we have in Python. So please be with me, and please, I know it's the end of the day, but let's look at this code and tell me. This code is very simple. What's the problem here?
It doesn't return.
It doesn't return. But because it's Python, if no one uses this function, and only somewhere in production, in some code branch, you get to this function, only then it will fail. So it's a big problem. I fixed it. There's a return. What's wrong with it now? Will it work? Yes. Yes, it will work. Because Python is horrible dynamic language that says, hey, I have B in my scope before I started using this function. So probably you mean this B, right? I will do it for you. And it will actually return what you think it will return. So this is really, really bad. You have to... I had like a problem like that, and I debugged it for 2 days because there was a parameter that I forgot to provide to a function with many, many parameters. And there was in the main block of it exactly the parameter with the same name, so I decided to take it. And it was a totally different thing. Okay, who knows what is this? What is this number? Max int 32.
Max uint, I guess, rather. Yeah.
Yes, max uint 32. Great. So we are creating a function here that takes a number and adds a number and returns it, and then we are using it with what is this and 1. What will be the return? What we will see when the print, with the print, sorry.
It's arbitrary decision.
No, it's not arbitrary decision. It expands. It expands it. It says, hey, it's max uint, but don't worry, I'm a dynamic language. I will give you uint 64. You are good. So we are, as a C++ programmers, we are saying, okay, we need it to be 0 because it wraps around and it's 0. No, it's not 0. It will be uint 64 here. As C++ programmers, we sometimes want to work with binary blocks, right? With bits, we want to move them, do things with them. And actually, Python provides a cool thing that's called bin. It returns a binary type. But if we will look closely at the type of bin, we will see it's a string. So working on bits in Python, it's not really working on bits. It's working on bytes, and you're spending a lot of memory and spending a lot of time. And I actually saw things in code that are bloating memory because they're wanting to work with bin operations, and they're paying for it with time and explosive memory. But not everything is bad. Like C++ that is growing and becoming better and safer, Python is growing and becoming better and safer. Here I want to show a couple of things that we got in Python, modern Python, that actually helps us with it. So since Python 3.10, we have typing. We can hint to the interpreter what we want to use. Here we have the function, exactly the same function, but we are saying, hey, A is supposed to be an integer, B is supposed to be an integer, and I'm returning an integer. So if you get anything else, that's wrong. And here, when I try to use a floating point with it, it says a nice warning. I expected an integer, but I got a float. It's a warning. You have to see what the IDE does. If not, that's a problem, still. If I forgot the return, instead of waiting for some code block that will explode somewhere later in time, I can see the actual warning here. So it's much easier to debug. In Python 3.12, we got typing, which is even more cool. We can do generic functions. So Python is becoming more like C++ as well. It's a templated function. Here we are saying that foo is a function that templated on t, and t can be an integer or a string. And then the parameter a that is using, it's a list of those t's, and b is t as well. And we will return list of t's. Inside the function, this is not scary anymore because we know that a is supposed to be a list, so we can use append on it. We're using append safely because we know it will be a list. And then we're returning a. If I will use it like that, I will say foo with 1 and 2 and 3, everything is fine. The IDE doesn't yell at me. But if I will try to use float, it will say, wait a minute. You told me that you want this list to be an integer or a string, this type t, to be an integer or a string. Float is not an integer or a string, so please replace it. Another cool thing is type. Type is using in C++. So we're using here. We're saying that u of type t, that u is templated on t, is basically list of anything or a tuple of anything of any size. Then we are using the function, and it's easier to read because we're saying it's a is a type of u, and we're returning a list of u's, and we're returning a list of a. That's it. Really simple. And we can use it like that. It's safe, it's simple. It adds a lot of safety to the code. But as I mentioned, those are just warnings. And warnings are not enough. You need to go to your DevOps team, if you are using Python, and to tell them, hey, we need MyPy or any other type checker inside our CI, because failing in CI is much better and easier than failing at a customer. Here we have an example of the code that takes something and adds a string to it, but the something is an integer or a string, and we're returning this list, and we're adding a floating point here. So what it says is, wait, you have a problem here. And if we run MyPy, instead of just warning us, MyPy will say, hey, you have an error. You need to fix it right now because you are doing something that is incorrect. So it's much better and safer. I'm sorry for using Windows. My machine with the GPU is Windows machine. But that is not enough as well. And here comes the fun part. What will be a C++ conference without saying Rust a couple of times? So here I'm saying Rust is a linter that was written in Rust. And it is a very good linter, it's very fast, and it does a great job. So you need MyPy and the linter. Why do you need the linter? Because MyPy didn't see another problem here. Do you see then the other problem? Basically, we have a logic problem. We cannot do plus equals on those things. And the linter, MyPy cannot see that, but the linter can. Another cool Rust thing is UV. So basically, who is using pip? Whoever used Conda. What do you think about Conda resolve?
Awful.
Thank you. I would say throw it in the garbage. It's so slow. It sometimes, if you have a lot of packages, it takes minutes, like 25 minutes. In my case, it was 35 minutes. I started to move everything to UV, sorry, and it's amazing. The timing became much, much faster. You can see it in the example that they are providing that pip is almost 5 times slower, even more. Conda is 500 times slower, but this is amazing. And it actually works, and it's easy to use. And if you want to use it, you can scan it later and read more about it. And if you use Python, move to UV. Now, let's talk about performance. Not just safety is becoming better. As Python becomes more modern, it becomes faster as well. So here we have a comparison of Python versions until Python 3.11. And as you can see, in each of the benchmarks, the performance of Python 3.11, it's much, much faster. When we will see the comparison of Python 3.11 to Python 3.13, we can see that Python 3.12 done almost nothing performance-wise. They had the little bugs that they fixed. But in 3.13, they actually gained 5% more, 6%, something like that. And they even have a version without the horrible GIL, but we will talk about it later. Now, another important thing is when we think about Python, we say it's an easy language, anyone can write it. You don't have to understand what you're doing. Everything will work. But if you want something to be a little bit more performant and do the correct things, you need to think about the inner mechanics. So here we have just a very huge list of numbers and two functions. Function A is just summing up with a loop, and function 2 using the built-in function sum. Then we are running it for 100k times. Which function will be faster? A or B? 1 or 2? 2. Very good. It's 4 times faster. 4 times faster. Why is it faster? Because sum is basically written in C. It's written in C, it knows better about your collection, it knows how to sum it better, it knows about hotspots and caching and all of those things, so it runs it much, much faster. Another thing that you get here is that you are not using loops inside interpreted languages, because loops and branches inside interpreted languages are horrible. They take a lot of time. We can get better. Who used NumPy? Hands? Cool. So NumPy is a great tool. Let's do the same thing with NumPy, where instead of creating a Python list, we're creating an ND array of 100k elements, random elements, and we're summing them up with npSum. And it's 3 seconds. It's 3 seconds, that means it's 11 times faster than the built-in function. And why is that? So NumPy is an abstraction over ND arrays. It has a really easy API. It's great for math functions that are doing things with arrays and tensors as well. Arrays are not dynamic. Each array that you are creating, it will not grow anymore. So it's more C-like. And the core implementation behind the scenes, it's C and C++. Most of it is C because it was written way back. But the new components that they're adding, they're becoming C++. So it was pretty cool for me to see that. And behind the scenes, they're using AVX, and they're doing multiple multiplications, and they're actually understanding what a CPU you're using and doing a lot of work for you to get faster. But again, we have to understand how NumPy works. So NumPy is very easy to use, and it has a nice API that says, give me an ND array-like, and I will work with it. A list in Python is an ND array-like. So let's do an example here. We have the function with the sum, which is a built-in function, and we have function 3, which is using NumPy on this regular Python list. Which one will be faster here, 2 or 3? 2. Great audience. 2 is faster. Why is 2 faster? Who can answer that?
It's a guess. It has to convert array type repeatedly.
It has a huge overhead. Basically, it copies the list into the ND array, moves it to C++ memory, C memory, works on it, returns it to list, and vice versa. So it takes long, long time to do it. Okay. So what do we take away from this? We always need to use things that are already created. We don't have to recreate things in Python. We have great and major libraries that do things for us. We don't have to do them all over again. But you do need to understand how those libraries work. You need to understand how Python works, because yes, it's a simple language, but sometimes you need to take more from it to make it even better. Don't abuse nice APIs, because Python is written for people that don't know how to write code, and they always give in nice APIs, and then people are shooting themselves in the foot if they don't understand the API and the library correctly. As I said, let's use more libraries that are already there, more modules that are already there, but sometimes you can't. Sometimes you have to create something of your own. Let's say that our algorithmic team, we have created this cool function that you all will sign an NDA after this. It's a proprietary function that makes amazing things. I will not say what. And they want to test a new algorithm with this function, but they have to do this function exactly the same. They want it in C++. Luckily for us, Python interpreter, CPython, is basically a C program. Yes, there are different interpreters, like Cppyy, which is much, much faster, but it's not complete yet. So we will talk more about CPython, which is more distributed and more people are using it. Because it's a C program that maintains a state of the whole program that you've written in Python, and it uses PyObject, it's really easy for us to attach to it, basically creating in SO files. Here, if we will look at how things look schematically, we will see that we have the interpreter inside the CPython core, and we have everything becomes a PyObject. We have inputs and outputs. The interpreter is reading our script file, creating the PyObject, and maintaining the state. As I mentioned, to do that, we have, to create SOs, we have a Python H file that is provided by CPython. Python H file is basically an API to Python. How Python is written, we can just hook inside Python and create our own functionality and do whatever we want with it. So if we will do that and we will use it, we will get something like that. Our core operation is almost the same. The script is written almost the same, but we have an external SO that is connected to the PyObject that is created for it, and it will be used in the state of the program. Sounds simple, but what do we need to do to actually hook to it? We have to include, of course, python.h. We have to write our C function here. Then we have to do a wrapper for CPython. The wrapper, of course, returns PyObject pointer. It receives a self object because every Python function has a self object in it. And it receives PyObject arguments. So all the arguments are one parameter. We know that this function has only two arguments. So we're saying int a and b. We're extracting or parsing the tuple of the arguments into a and b, actually using the foo function inside it, because we can do it, we can see it. And then we are returning a pyfloat from double, because it returns as double and we want it to be a float, we are creating it. Afterwards, we need to create a foo methods. Foo methods are the methods that will be used inside the module. So we're creating it and we're saying, okay, we will call this function foo. It will use pyfoo, the function that we are created. It's met vargs. We are saying what the documentation for the function. We're using Sentinel, a weird Sentinel. And then we need to create our module. So when we're creating the module, we're initializing it. We're saying what it will do. We're saying what its name. We're saying here that it will be global. And it will use foo methods in it. This function is the most important function to understand. When you do import inside your Python code, this function will be called. So when this function is called, it's basically telling it, I need foo module to be created inside Python. And the naming is really important. So your module has to be the same name as you are calling it here. We are not done. Because we have an extension, our setup file is not exactly the same setup file for any module that we are doing. So we're importing extensions. We are creating a Python extension here that's called foo module. We have the source provided here that is foomodule.c. Then we can do our normal setup for the module itself. And we're just saying inside it that external module is the module that we created. I don't know about you, I'm a lazy guy. That's too much code to write, boilerplate code to write, to do binding for one simple function. So luckily for us, there are many, many different binding tools out there that can help us with that. We can actually use those binding tools to get what we want. I don't have time to show everything, but I will mention PyBind 11 and Boost Python. Those are the oldest libraries out there to do the bindings. They made things much, much easier because you could just write C++ code like C++ extension and compile it to be Python, compile it to be a library, and then attach it to Python. I will talk about Cython, which is an amazing tool. It's a rich language that lets you write Pythonic code, and you can run Python in C++ and C++ in Python. You can run Python in C++ with it. And you have another thing here, which is a jewel. It's called CppYy. CppYy is a dynamic binding library. It's amazing. It's basically made bindings easier, faster, and if you only need to use something that works in Python and run C++ code, this is the way to go. But Cython is not far behind. Now, what about performance? The code that I showed you, if you run it in C++, it's 4 milliseconds. Nothing. If you will run this function in pure Python, it will run for a second and 2 milliseconds. That's a long time. 200 milliseconds, sorry. If we will do the CPython code that we've done and we will run it, it will run in 1.1. So I think it's noise because CPython doesn't do anything here. The Python code and the CPython code should do the same thing. PyBind 11, which is so cool and nice, runs 5 times slower. Why is that? Overheads. Yeah.
I was going to ask, like, are we benchmarking interpreters?
Microphone.
Oh, sorry. I was going to ask, are we benchmarking interpreter startup time as part of this? Or
No.
Oh, we're not.
No.
Wow. Okay.
No. It's pure. The interpreter already started. What I did in Python itself is using timeit. So timeit is starting after the interpreter started. We have overheads. That means that we always copy things to Py objects and vice versa. Different libraries do different things to do this. And PyBind 11, for some reason, decided inside their design to do everything on the heap. So your heap is always growing and retracting, and you have vectors inside it to grow and retract, and it takes time. And just like in CUDA code, you always have to think about hotspots of code. So you cannot push something to CUDA that does just one calculation and say, yeah, I'm using CUDA, I'm so performant like now. No, you have overheads to go over PCI Express. Here we're not going through PCI Express, but we are doing cache and we are moving inside the memory. What can we do to make it better? Make batch functions. That means prepare a lot of data and send it to the function. Don't use one calculation. Use binding objects. For example, you have array_t. Array_t is something that's already bounded. You have it inside Python, PyBind 11. It's already bounded to ND_array. So you can use that to make your code faster. Return values, and this is really, really important. If you're doing bindings, Python is a garbage collected language. Garbage collected language means that if you return something from Python to C++, Python may decide to delete it. And then your memory will be corrupted. So always return with smart pointers, and this smart pointer should be a shared pointer, of course. This is an example of using an ND_array inside the C++ code. So it looks almost exactly the same, a little bit more harder to understand in my opinion, because you have to request and extract the internal pointer from it, and then run on the internal pointer. It's harder to read, and that's the reason that I don't like to write C++ code that looks like that. There are better tools for it. If you can, just use other languages, other extensions or languages. But if we will look at the performance for that, PyBind 11 now runs 1.6 seconds. It's a lot faster. And that's because we removed the overheads. Now let's talk about Cython. Cython is great. As I said, it's a rich, rich language that almost Pythonic-like. It has much more features than any one of those, PyBind 11 and Boost Python. You can do almost anything you want. And we can, the jewel here is that you can run Python code inside C++. And sometimes it's really important when you have interops. For some reason, many people, when they see Cython code, they're getting scared. I don't know why. We will see Cython code, and you will tell me if that's scary. Everything starts with a C++ class. We have a C++ class inside the namespace important. We have virtual functions foo and bar, and we have our virtual destructor. We have a struct real that publicly inherits from abstract. We are actually defining the functions here and creating them. Inside Cython, you have two levels as well, like C++. PXD files are files that are resembling H files. So here you're saying, what are your declarations? Here we're saying we have cdef extern that's saying, please import from class.hpp, the namespace important, we will use the whole namespace, and then we're creating something that's called cdef C++ class. C++ class, cdef C++ class, it means this is a class that's written in C++, and those are the definitions that I want to take from this class. Then we're creating the C-real that inherits C abstract, and of course we have the declaration for real, for the constructor, foo and bar functions here as well. Then we need to create an actual class with the bindings. So it's a cdef class. Cdef class means it's like a Python class, but it has C++ or C members inside it. And here we have a member that's called C-real, and it's a shared pointer. Now, PYX files are files that are like C++, CPP files. So here we're saying from my model that I created, the PXD file, I want to C import all the things that I defined. So I want to bring everything in. The cool thing about Cython, they wrapped almost the whole standard library. So you can use almost the whole standard library inside your Cython code. You are doing, here we are importing make shared and null pointer. Cython, we also will have to import from operators, we have to import the reference. And we have to import the reference because we will dereference a pointer. Why I cannot use an asterisk inside Python code? Who knows? Sorry? It's an operator. It's an operator that expands. So here we cannot expand, and this operator is already taken, so we can do the reference. And what we are doing here is basically we're creating the function that we want to bind, and we are saying we are dereferencing the C-real inside this class. We are getting the pointer out of it because we have this function inside shared pointer, and we are using foo function in it. Pretty simple. About the code, is it that scary? Okay. Someone thinks it's scary? Okay, cool. Then we have to compile it. Basically, it will compile. We are saying we want to do it in Python 3. We want to compile it to C++ and not to C. And the model that we will use is my model PyYX. And then, because it's so automatic right now, we can use CMake to do the work for us. What I'm doing here is I'm actually finding the package for Python libraries. I'm creating a custom command that will compile the Python code for us. It will create the CPP file, and I'm using the output of the CPP file to bind it to the add library. I'm adding the library, and I'm saying, okay, I need my model to be here. That means that my model needs to be created. That means that the custom command will be called. And the most important part here is that I'm removing the prefix that is created. And I'm removing the prefix that is created because, as I mentioned, the init of the module will use the same name. And if CMake will add the lib to it, we are doomed. And then we can write a simple Python install function that just takes the setup and install it. So it's simple, maintainable. You can use it inside your CI and you use it inside your code. Now let's look at the other way, Python to C++. Let's say we are working in an air-gapped computer and we cannot do anything. We cannot bring Conan, we cannot download any other modules, we cannot do anything, but we have Python. Python comes with JSON. And we really need to do something with JSON in C++. To write JSON in C++ without libraries, it's hard. So it's easier to do this, for example. Here we're creating a function, and we're telling Cython, create a C++ function for us from this Python code. So cdef public is basically telling it, create a C++ function. Then we're using the JSON. It's really easy in Python, and we don't have to do a lot here. We can save a lot of time. Inside your Python code, you will have to initialize the interpreter inside your C++ code. So we're DL opening the lib Python. We're bringing it in, we're initializing it, we're calling the initialize function, and this initialize function will call the function that is created in Cython, and we can start working. Few words about exceptions. There is no propagation between the two languages. So if you're writing Cython, you cannot throw just a regular Python exception and expect it to get to your C++ code. So what you need to do, there's a simple solution for it. What you need to do is create a simple C++ function that throws a simple exception in C++, bind it with CPython that looks like, with Cython that looks like that, and create a Python function that uses the binded C++ function. Easy, simple, propagates to everywhere. GIL. GIL is our enemy, and we hate it, and someday it will be gone. GIL is a global interpreter. It actually restricts threads from being run as threads in Python. So each thread, before it runs, it has to take the GIL, and that means it's sequential and not really parallel. In Python 3.13, they're supposed to remove GIL. They have a special build for it. They didn't remove it. And I assure you, this build will have so many bugs. We will have GIL for a long time with us. In CPython, we have ways to remove the GIL. In Cython, we have an easier way to do it. And I don't want to use CPython because it's cluttered, it's a lot of boilerplate code, and no one likes it. And inside threads, we can run without GIL. So let's look like let's see an example. So here we have an example that creates a function, and all we have to do in Cython is to say, no GIL, that's it. We have created a function that we're saying it will not throw, and we have no GIL in this function. Then we have another function where we are creating C++ parameters, arguments. We are copying Py objects into the C++ memory. We are saying, creating a block for no GIL. We are saying inside this block, we don't have GIL, don't take it. And we are using the function inside it. Then we are copying back the C++ object to Py object. Inside the main file, we are creating huge lists. We are running on this list, and for each one of the parameters, we are just creating a thread. It's faster than what we could get without using no GIL, but it still has GIL in a lot of places. So maybe I can save some of those things. What will happen if I will use the copy to Py object inside the no GIL code? Will it work? The answer is no. The moment you're starting to talk about Py objects, GIL will take effect. You cannot do that. You actually need to be inside a scope of C memory and C code. And now we're getting to dynamic binding. And this is basically cool. So there is a tool that was created by Clang called Cling. Cling is a C++ interpreter that someone took and made a library for Python from it. It's really easy to use. It has great features and many, many things that you could do with them, a lot faster, and the development is amazing. So here's an example. All you need to do to run a C++ function inside your Python code is to import cppyy, to use cppdef, to write your actual C++ function in, to access GBL, which is a global namespace inside cppyy, and to use the function. That's it. Performance-wise, we got under a second. This is much nicer than any other library that we've seen. We don't have to install Clang. We don't need to duplicate STL because we're just using STL. That's the fun part about it. Full support of templates, full support of inheritance, full support of callbacks and lambdas. It does everything that C++ does. Here we have an example of almost the same thing that we've seen before. We have an abstract class, we have a real class that inherits from the abstract class, and we are defining the functions. To use it, all we have to do is to import cppyy, include the H file, everything will be interpreted, to use from GBL to import real, and then we can just see that real is a class, a Python class. To use it, we have to initialize it, and then just to use it. That's it. As simple as that. We can do cross inheritance. So we have an abstract class that we wrote in C++, but we want to do another class inside Python, but we can use the C++ class to be the father of this class. So here we have a PyReal class that inherits from the abstract inside GBL, because GBL creates something that is bounded to actual Python. And we redefined in the functions. Another important thing here is that we are including array, which is just an STL code. And we are using GBL array, and we are creating a C++ array inside our Python code, and just using C++ inside Python directly. Templates. It actually understands and interprets templates. So even template is hard as this. Basically here we are calling a function that's called that expects to get a callback function, a function pointer, and a list of arguments, and then we are using std_invoke to invoke the function. Here's the cool part. I can actually provide a Python function into the C++ code. So here we are creating a function with 2 integers and a float, and we are providing it to a call-it function that we have created inside GBL, and it actually works. The important part here is that you need to help the instantiation of the template. Python is all PyObjects, but when we are using typing, we are helping it. We are saying, okay, please instantiate the template with int, and return type is float. Only then it will work. But still, it's cool. Sometimes you need to work with external libraries, so you don't have everything. So let's create a simple external library with a function foo, and we have the code for the function foo, which is really nice. Then we're compiling it and creating an SO file out of it. And then to use it inside inside your Python, you're just saying, okay, cppyy, include my interface, load library that's called end.so, and use the foo function. That's it. You have a library. Sometimes libraries don't come as SOs, and you have static libraries or archives. So you have 2 ways to deal with that. You can decompile the archive and create an SO from it. It's hectic stuff, don't do that. But you can just relink it. You can create your own library that has nothing inside it, and you're just linking to the A library, to the archive, and it brings all the symbols into your library, and you have an SO. So it's as simple as that. Moreover, you have everything that you have to provide to the C++ compiler, you have to provide to clean. So if you are not using include paths that are in some path, and you're not using the library paths in some default library path, that LD library path, you can actually provide and say, my libraries are there, please look there. And it can be a list of directories. So it's really cool as well. GIL, we talked about GIL. Here it's even easier. So we're creating a C++ function that just sleeps for a long time. Every GBL object has something that's called an attribute that's called release GIL. All we have to do is to say release GIL true. That's it. And when we are running it and creating threads, basically this code says that I will not take the GIL. Not everything is fine and dandy. Most of the things work, but bit fields don't. So if we are creating something like that, and that's funny, this is a bug that was opened for Cppyy for a long time, and the creator of Cppyy actually wrote, I knew this day will come. I knew this day will come. Bit fields. So if we will use it, we will just including these bit fields, we are creating it. But if we want to print it, you see bogus, it's nothing. Python cannot reprehend what a bit field is. So because of that, it's just printing nothing. The good part is it's easy to fix. Because the memory layout is correct, all we need to do is create a C++ function that takes our object, interprets it to 2-byte string, and then just to print the bytes together. And if we will do that, we will get exactly what we wanted. The function looks like that, but I want to jump over it because I want to show you a couple of things with reflections. Those are the important things to understand. Operator that takes something and returns a meta info. The operator with the brackets, it's something that takes some object of meta info and creates an instance of it. Template for is really important because it's something that runs over our const-eval code and instantiating code for us. And all reflections should be done in compile time. So let's look at something like that. We have a namespace with 2 functions inside it. We want to bind these functions. I will use pybind11 to do it because it's easier. So to do it with pybind11, you have to do something like that. You have to create a pybind module. You have to do documentation to create a submodule inside it, to use def on 2 functions. And as you can see, there's a lot of boilerplate code here. With reflections, it becomes something that is more concrete. So here, we have to take the context out. We have to create a static array from a function that's called members of. Members of will take everything from the namespace and provide us with the meta info objects. We will run on this meta info objects with a static array of those meta info objects. And we will say, if this meta info object is a function, we will create an identifier from this function that means a name. And then we will use the definition inside the pybind. And we will say, okay, fn data, this is the name of my function. And R is the actual object that I want to instantiate. So it's providing the actual function pointer that we will use. Now, if you want parameters, it's a little bit more complicated, but it's doable. And again, you can write a block of this reflection and to do it for any block of binding that you want, and it will save you a lot. It looked in the previous slide like it's a lot larger, more code, but it's a generic code that works for everything. You just need to provide a meta info, and for any meta info, it will work. To do it with pybind, for what I just showed in namespace 2, it looks almost the same, but you actually have to use pyargs to provide the name of the arguments inside it. To do it with reflections, we have to access context. We have to create our context. We have to create our symbols like we created them before. We have to create the submodule like we created before. But here is the tricky part. We have to run over all the symbols. We have to create a static string from the identifier of those symbols. We have to create all the parameters. So we don't have this function yet. You can do it in different ways, but it should be there soon. Parameters of. Then we are creating a lambda that will expand all our arguments. And this lambda is basically going on the namespace object or the meta info object, creates an array of strings of all the arguments because it expands it with the fold expression. And then it defines all the functions with all the arguments. As easy as that. It's something that is more hard to understand right now because reflections are really new, but it makes things simpler. It removes all boilerplate code and it makes C++ even stronger. So in closing notes, use bindings. Sometimes to use Cython, it's easier to make your code work faster. Sometimes without doing anything, just Cython, your Python code will make it faster. Always understand your APIs. Don't abuse your APIs. use batch functions, understand how Python works, really avoid dangling pointers, and I think start looking at the reflections because they're going to be very, very important in C++. Thank you.
Hi. Great talk. One thing I was wondering about, so for CPython specifically, I just wanted to restate that I did verify that I had understood. So it basically it uses the C++ interpreter inside of libclang, like it binds to that directly, essentially. So
It installs with it the binding of cling into Python.
Okay.
And you get it exactly when you install this module in. So you don't need to do anything. You don't need to have Clang on your computer. You don't need those things. You just need the library. That's it.
The main thing I was wondering about is just that it's built on top of the Clang implementation.
Cling is built on top of Clang.
Okay, that's what I'm saying is that at the end of the day, it's using the interpreter inside of Clang. So basically, anything that Clang can compile, this thing should be able to work.
Yeah, that's what's cool about it.
Yeah. Thank you.
Anyone else? Who has that? If you can come to the microphone, please.
Hello.
Yes.
Thank you for the talk. What about nanobind?
Nanobind. I have no experience with nanobind, but it's really similar to what PyBind and other static libraries do. So I don't expect it to be a lot better.
Thank you.
What's been your experience for the debugging across those language boundaries?
With which tool?
Yes.
With everyone. PyBind and Boost Python are the easiest one. Cython is a little bit harder because you have to pay to have a debugger for it. So debugging is usually done with printing. It's doable. And with CppYY, it's actually if something crashes, if something's done wrongly, you will get a Clang message out of it. So it will say, I couldn't compile it because something happened. I couldn't do that because something happened. Something didn't run correctly. So it's cool.
Thanks.
Great talk. One of the problems that I've been having with static linking Python to C++ Python is because I need a different compiling for each Python version. Do you know any other way to do that?
What do you mean with different compiling?
Not compiling. For example, if I want to use the CPP code in Python 3.12, I need to compile it for 3.12. And every time I need a new version, I need to recompile my code.
If you're doing it with a different library, then yes, because you already took the symbols. You actually linked yourself with python.so.
Yeah.
So if you have a different one, there's not a lot to do. The only thing I can say, use CppYY. You won't have to do that.
Thank you.
So I guess that's it. Thank you, everyone.